Hey everybody. Today we're doing an important integral test example, the p-series. Let's start by reviewing the integral test. We're looking at some series, n equals 1 to infinity, a sub n, and we'd like to know whether it converges or diverges. So let's imagine a function f of x that agrees with the sequence an on the positive integers. Basically, that just means take the formula for an, take out the n and replace it with x. View it as a function that's defined not just on the positive integers, but on all numbers greater than or equal to 1. If this function is positive, decreasing, and continuous on 1 to infinity, then instead of looking at the series n equals 1 to infinity an, look at the improper integral 1 to infinity f of x dx. If that improper integral converges, so does the series. And if it diverges, so does the series. It doesn't really matter if you start at n equals 1, could be any other value, n equals 0, n equals 10, whatever. And it's also okay if the function f of x doesn't start out positive, decreasing, and continuous, as long as it becomes positive, decreasing, and continuous eventually, and then stays that way. So what's a p-series? It's a series of the form sum k equals 1 to infinity, 1 over k to the p. So p is just some fixed number here. You might have the sum of 1 over k squared, or the sum of 1 over the square root of k, for instance. Does it ever converge? And if so, for which values of p does it converge? That's the question we really want to answer in this video. Right away, we have a partial answer. If p is less than or equal to 0, the series diverges by the test for divergence, because as k goes to infinity, 1 over k to the p in that situation doesn't go to 0. For example, if p is 1, you're just adding 1 plus 1 plus 1 forever. So we're really only concerned about positive values of p. Now we're in a situation where the integral test is going to help us. We have this function, f of x equals x to the negative p greater than 0, and it's going to be easy to integrate, and it's positive for x greater than or equal to 1, continuous because we avoid the vertical asymptote x equals 0, and it's decreasing. So here's where it matters that p is greater than 0. If we take a derivative, we get a negative function, and so f of x is going to be decreasing from 1 to infinity. So we're going to determine the convergence of the series k equals 1 to infinity, 1 over x to the p, by looking at this integral, 1 to infinity x to the negative p dx. It's an improper integral, so the first thing we want to do is to take out that infinity, replace it with an r. After we do the proper integral, 1 to r, we'll then take a limit and let r go to infinity. So we get an antiderivative, raise the power by 1, divide by that new power. Notice that's only valid if p is not 1. If p is 1, you're dividing by 0 here, so that antiderivative is not true. So we'll have to cover the p equals 1 case separately. Now plug in the limits of integration and ask, for which values of p do we get a finite value as r goes to infinity? The answer is that if p is greater than 1. If p is greater than 1, then that exponent on the r, 1 minus p, is going to be negative. And so as r goes to infinity, that'll go to 0. On the other hand, if p is between 0 and 1, that exponent is positive, and so as r goes to infinity, r to the 1 minus p will also go into infinity. So overall, we get convergence when p is greater than 1, divergence when p is less than 1. So let's go back and look at the p equals 1 case. So we're doing the limit as r goes to infinity, integral from 1 to r, x to the negative 1 dx. Now the antiderivative that we want is the natural log of x. Plug in the limits of integration, remembering that the natural log of 1 is 0, and then take the limit. As r goes to infinity, the natural log of r goes to infinity too. So the p-series diverges when p is equal to 1. This isn't surprising. When p is 1, we've just got the harmonic series, the sum of 1 over k, 1 plus a half plus a third, and so on. And we already knew that one diverged. Overall, the p-series, sum k equals 1 to infinity, 1 over k to the p, converges exactly when p is greater than 1, and diverges when p is less than or equal to 1. This result is really worth remembering. It becomes very useful when we start doing comparison tests in just a couple of sections.